For anything at all to happen in the universe, a force must act. For anything at all to happen in the universe, a force must act. We usually think of forces as moving things around, pulling this apple towards the ground or pushing a car up a hill. But forces also cause the sun to shine. They make the ice melt in your drink, and they cause a plant to emerge from a seed. Forces are the agents of change in the universe. To help us understand forces, thousands of scientists around the world have spent billions of pounds to build this machine. I'm standing 100 metres below the ground at CERN in Geneva, and this is the CMS detector, part of the largest and most complicated scientific experiment ever attempted. This experiment will give us deeper insight into the forces of nature than ever before. It's a long way from when Isaac Newton pondered the laws of gravity, but all part of the same story. We understand the world today in terms of four forces of nature: the strong and weak nuclear forces, electromagnetism and gravity. Now, gravity is perhaps the most familiar, but in fact it's by far the weakest of the four forces. So weak, in fact, that we can completely ignore its effects when we explore the subatomic world, at least with today's experiments. Besides the familiar but weak force of gravity, there are three other forces in this universe, each of which is vital for our existence. Now, it may not seem obvious, but the force that holds these bubbles together is the same force that allows this flame to burn. Electromagnetism. It's the force that allows us to push and pull things, the force that allows us to see everything in the world around us, and the force that allows your TV set to work. Electromagnetism is the force that holds electrons in place around the atomic nucleus and holds the atoms and molecules in place in my body. It also causes electrons to repel each other. So even though the whole planet Earth is pulling the apple down to the ground, the apple stays firmly in my hand because the electrons in its surface are repelled by the electrons in my palm. I've used the word electromagnetism to describe a single force, but electricity and magnetism seem at first sight to be very different phenomena. The magnetism that makes this top levitate seems to have nothing in common with these electrical sparks. The Greeks knew that if you rubbed a piece of amber with fur, it would pick up feathers. They also knew that certain rocks attracted iron, but they had no idea that the two were related. The two forces of gravity and electromagnetism seem at first sight to be sufficient to explain everything we see or feel in our everyday world. But once we look inside the atom, it is immediately obvious that other forces must be at work in the universe. By the mid-1930s, we knew that atoms are composed of electrons orbiting a nucleus of protons and neutrons. But there's a problem with this model because protons are positively charged. And so when they're close together, the electromagnetic repulsion should blow the nucleus apart. And that's not what happens, of course. There must be another force many times stronger than electromagnetism that glues the nucleus together. And that force is called the strong force.
The strong force is not only responsible for holding the nuclei of atoms together, and without that, every atom in the universe would just spontaneously explode. But it's also, and this is quite interesting, responsible for 98% of nuclear mass. That means 98% of my mass, your mass, the mass of the Sun, the mass of the Earth. And we don't quite know exactly how the strong force generates that mass. And so we want to study that in more detail.
The discovery of the strong force was a giant leap forward in our understanding of nature. But there were still phenomena that we couldn't explain. This is a PET scanner, and it's transformed the way we diagnose many diseases because it allows us to look inside the body and detect abnormalities in cellular activity. Machines like this were developed as a direct result of advances in particle physics. The P in PET stands for positron, an antimatter electron, identical in every way except it has opposite charge. Positrons or electrons are emitted from the nucleus in radioactive beta decay. And that's a process that baffled physicists throughout the early 1930s. And they knew that the nucleus was made up of protons and neutrons held together by the strong force. And they knew that beta radiation came out of the nucleus. They also knew that beta radiation was comprised of electrons. So where did the electrons come from? It was the Italian giant of science, Enrico Fermi, who finally solved the problem. In 1934, he proposed that there's a weak nuclear force that can convert protons into neutrons or neutrons into protons, at the same time emitting electrons or positrons and neutrinos from the nucleus. Fermi had found the missing force that explained the inner workings of the atom.
He played a huge role in nuclear physics, and his weak force has played a huge role in us being here. In fact, it's critical that it's so weak because it controls the first stage of the Sun's fusion cycle. Because it's weak, the Sun only just keeps alight. It's been burning for 5 billion years already. If the weak force had been any more powerful, the Sun would have burnt out before any of us got here.